how come we know about this particular feature that is called the neutrino oscillation? Well, neutrino is a very exotic particle that belongs to the leptons group and which have a very interesting property that it has almost negligible, I mean, very low mass, and it interacts with the matter weakly, and it travels at a speed of light. And therefore, the information that it is carrying from the very deep universe to the Earth is almost undeviated. Most of the time, like photons and electrons, high energy particles that we usually detect is almost deviated by the is almost execute the this uh, electromagnetic interaction, mostly the photon. So the information that we are gathering from the photon is somewhat deviated. However, the neutrino telescope, the information that we are getting from the neutrino telescope is almost giving us absolute information. Now, interestingly, it also have a very interesting property that when the neutrino traveling from one place to other, it changes its flavor state. Like when it started from the core of the sun and it detected, hello, and it is detected at the earth, the flavor state of the neutrino got changed. Now, how come we know that? See, in the first video, we are watching that there are plenty numbers of neutrino is emitting from the sun. And what people initially did that they have created a huge tank of chlorine. And when the neutrino hit that chlorine, it transformed the chlorine to the argon. And the amount of argon fetched in 1 year will be the amount of neutrino detected. But interestingly, the theoretically estimated number of amount of argon that we should get is almost one-third amount we are actually getting after the experiment is over. So uh, this intrigued the question that where does this two-third number of neutrino is actually going? This is called the famous solar neutrino problem, which first introduced the concept of neutrino oscillation. That means this two-third amount of neutrino, since our detector is sensitive to detect only the electron flavor of neutrino, this two-third amount of neutrino is oscillated to the other flavor, that is converted to any other flavor, that is muon and tau. So this was the first time that we know that neutrino is actually oscillating, and which got the first Nobel Prize in 2002 for this solving this solar neutrino problem. And later on, experimentally in the T2K experiment in Japan in 2015, it has experimentally proven this particular phenomenon of neutrino oscillation. Not only that, we also observe the same kind of signature for the atmospheric neutrino as well. So now, what is the neutrino oscillation? The oscillation refers to the way the neutrino change its flavor as they travel. A neutrino born as a flavor will eventually morph into the other varieties, and probability of appearing a particular flavor dependent is now it has gone to any other flavor dependency. And this oscillation phenomena is particularly give the signatures that neutrino do have mass. Previously, neutrinos are considered as massless in the standard model. But this is the first and evident signature that neutrino do have mass, which encompasses to the fact that we have to extend our standard model and go beyond the standard model, that is BSM physics. Neutrinos do have mass and they are coherent or incoherent nature. Initially, they are considered coherent nature, and They remain coherent after a certain distance of travel, and they are the first evidence of uh, physics beyond standard model. So this introduced that the neutrino does not have a particular mass. There are three kinds of neutrino and three flavor and three type of masses, nu1, nu2, and nu3. And flavored states are actually the linear superposition of the mass eigenstates. And when the neutrino is created, it's created in the flavor eigenstate. When the neutrino is traveling, it transforms into the mass eigenstate. And again, when the neutrino is detected in the detector, it again changes to the flavor to mass to the flavor eigenstate. So the neutrino have the two bases. One is the mass basis and other is the flavor basis. And these two basis set are interconnected by the UPMNS matrix. And this continuously interchanging of uh, detection to propagation and uh, production to propagation and propagation to detection gives us this phenomena of neutrino oscillation. And what is the outcome of the this oscillation phenomena? Well, any quantum mechanical phenomena, the outcome of any quantum mechanical phenomena is the probability density. And that is why what we get for the this neutrino as well in the detector, we do not detect the neutrino. We get the event rate. That is the probability of detecting a certain flavor states. So this is the core concept of the neutrino oscillation. Well, let us first start with the two flavor neutrino oscillation. That is the this is governed by the very simple mathematics, and it is actually defined by the Schrodinger equation. And the time evolution of the flavor state will give us the appearance probability that is given by the P alpha to, sorry, this has to be alpha to beta. Sorry, appearance probability is alpha to beta, that is appearance of the other flavor state, which is given by the sine squared 2 theta into sine squared delta n squared 2 1 L by 4E. So this theta is given by, is theta is defined as the mixing angle. And what is mixing angle? You can visualize in this way that when we rotate, it is a two-dimensional rotation kind of thing. And for the three flavor case, you can imagine it in such a way that it can be considered as a Euler rotation. And although there is a one difference is that for three flavor oscillation, since neutrinos are the leptons, there is an associated delta angle, that is delta Cp angle, which governs the matter-antimatter asymmetry, that is matter-antimatter asymmetry in the neutrino sector. It also carries the signature, you can see that delta n squared 2e, that is the mass square differences of the neutrino. And this mass square differences of the neutrino is for the solar neutrino is of the order of 10 to the power minus 5. And for the atmospheric neutrino, it is 10 power minus 3 eV square. And E is the neutrino energy and L is the baseline length. Similar way, since from the probability conservation, we can deduce the disappearance probability, that is vanishing nature of one particular flavor that we are expecting. And if we plot it, then we will get a signature of this oscillatory patterns. And experimentally, if we observe it, it actually gives this oscillatory pattern as well, which we will see later in this talk. Now, why do we need this quantum information? Like we all know, quantum information theory or quantum computing is a century-old journey starting from 1922 to 2016, where First, the Stern-Gerlach experiment has been done for the neutrino, and in 2016, it has uh, practically executed using the Cooper pairs in IBM-Q. Now, why this concept of, let us discuss in a very short way, why this particular concept is coming to the picture, that why we are interested in quantum information and why we are interested in neutrino as well. Well, let us think of this particular experiment. Consider this experiment as this is a black box which have a explosion inside, and due to which two particles are traveling equal and opposite direction in at the same time. In the right hand side, we have a device that measures the momentum of the particle. In left hand side, we have a device that can measure the position of the particle. Since the two particles are traveling just opposite to each other in equal time, so we can see that the person who is measuring the momentum of one particle readily guess the momentum of the other particle which is traveling in the opposite side, right? Because it will be just the opposite with a minus sign. It will be just same in the magnitude with a sign. And similarly, the person who is measuring the position of the particle will also have the same uh, guessing measurement of the position of the other particle. So this raises the question that uh, which is famously known as the EPR paradox, which questions the fundamental principle of Heisenberg's uncertainty on where the entire quantum mechanics is actually developed. So they propose that if we consider this particular experiment, then you can measure the position or momentum of a particle simultaneously. Then where does this Heisenberg's principle goes? To answer this question, various scientists come up with various answers, and ultimately, what the bottom line of entire discussion comes down is that although you can measure the position and momentum of the two particles simultaneously, you have to convey through classically from one person who is measuring the position and other person who is measuring the momentum classically. So this preserves the causality condition, number one. And number two, there is no guessing game. Bohr replied that there should not be any quantity. What would have been like this kind of term you cannot use in quantum mechanics. So after uh, this particular phenomena gives rise to this interesting state, which is called this particular phenomenon, which is known as the spooky action at a distance. That is, if we know the state of one particle, we can readily tell the state of the other particle. And if we know the state of the second particle, we can guess the state of the particle one. So there is a correlation between these two particles. And how do we quantum mechanically justify the state of these two correlated particles? This is called the entangled particle. See, it is given by this particular expression, given by this uh, state psi. So we considered, if we know that the two particles psi up and down of 1 and 2 are entangled and they initially belonged to the state psi. Now we are detecting, now in our detector, we are detecting a particle in the upspin of particle 1, then we can readily guess the other particle has to be spin down of particle 2 if they belong to this particular entangled state. So this is the very interesting class of states which is which gives a correlation effect between the two particles. Now, initially, the entire quantum mechanics we know that is given by the state vector. And state, a particular state, is actually the superposition of superposition is associated with the unit vectors in a Hilbert space, where the Hilbert space in general is the inner product space space where every Cauchy sequence in the space converges with respect to norm, defining an inner product. So, if, in a very easy way to understand this, a state psi is a superposition of uh, all the states that is spanning over the entire Hilbert space. Now, this is a simple superposition state. Now, if we considered an entangled superposition state, it is also a superposition state, but this is a non-factorizable superposition. So this is the conceptual distinction comes from the fundamental quantum mechanical superposition and the entangled superposition. Both of them are the outcome of the superposition state. However, any superposition state can be factored out, and but entangled superposition is the non-factorizable superposition state. And this is what we call the uh, this Bell states. Now let us come to this. In case of neutrino, we know that from the quantum mechanics, all the information about the particle is is contained within the state vector. But there is a distinction. If we have a number of particles, or there is a dissipation, or there is any decoherence effect, and entangled effect, or anything exotic is happening within the quantum system, then only the state vector cannot fully justify the information on that particular quantum state. There comes the rescue in terms of the density matrix. So density matrix is the most robust way to define a quantum system. Take this consideration in mind. Let us move forward with the definition of this particular entangled state for the neutrino system. Now, why we are interested with the neutrino? Because we know that this photon do execute electromagnetic information, and therefore there is a huge decoherence effect is appearing for the electrons and photons as well. However, for the neutrino, it interacts very weakly, and that is why it is very hard to detect. So the information that the neutrino will carry, if they execute, if they anyway they can construct a base state, it can carry that particular information undeviatedly to a large distance. So that is why we want to focus executing this quantum information analysis with the neutrino system. Now let us define first the state vector of the neutrino. Well, we have seen initially there is a oscillation phenomena is appearing for the neutrino system, and due to which there is a continuous flavor conversion is happening. Hence, we can define the state of the neutrino at a time evolved state by the occupation number probability of a particular flavor state. One depicts the occupation of electron flavor state, and 0 depicts the non-availability of the muon states, And 0e depicts the non-availability of electron state, and 1 mu depicts the availability of the electron states. Initially, the neutrino was considered to be only in the linear superposition. But let us consider that if they are in the entangled superposition, then what will happen? So initially, you can see that there is a interesting distinction that initially it is the linear superposition of this was the construction of the neutrino oscillation in time evolved flavor state. But if we consider there is a entangled superposition, or in the occupation number basis, if we represent this state nu e nu tau, then altogether we will get this to cube, that is 8 number of states. However, since neutrino are the fermions and there it is not, and they are executing intraparticle entanglement effect, it is not possible to have this 110 or 101 state, since they will violate the this Pauli's exclusion principle. So the flavor state that is important for the neutrino is 100, 010, and 001. Now, instead of having the three coherent superposition, single excitation subspace, now we have total 8 entangled mode states. Now, the question is how to justify this. They are really entangled or not? Or there are various ways to justify the entanglement measures available in the literature. However, in this slide, I have defined the flavor state of the two flavor for the two flavor scenario. But for the three flavor scenario, we have in total three different distinct states. And now, in order to have a overview of the how much these states are entangled, we will consider two different kind of entanglement. Uh, Tangle, then partial tangle, and ultimately a third kind of entanglement measures that we will introduce here is the concurrence field. Well, what is tangle? Tangle is a natural way to quantify the genuine tripartite entanglement in a three-flavor neutrino system, which measure the residual entanglement associated with a given flavor mode after subtracting all pairwise contribution. And if this tangle is zero, then if this tangle is non-zero, then it surely justify that the state is GHZ type of state. And if it is zero, then it signifies that it is W type of state. Now, for the neutrino, what we did that we reinterpreted this tangle in terms of the neutrino oscillation probability, and it in terms of the neutrino, and it is very nicely come out that it can be represented as the neutrino oscillation in terms of the appearance and disappearance probabilities. And what we found that it is it showing the nature that tau e is actually zero. Why tau e? Tau e signifies that initial flavor state is electron. And if we consider any other flavor state to be the initial flavor states, then also we are getting the exact same result. This signifies that neutrino cannot execute this Z type of entanglement. This signifies and encompasses towards the possibility that either it can have W type of entanglement or biseparable or separable states. To analyze further these two possibilities, we move forward for the partial tangle, and in the when we are analyzing with the partial tangle, then we are getting a non-zero value of partial tangle. However, in certain cases, we are getting, in certain areas, we are getting that this partial tangle may appear to be very low, that is very insignificant. So mathematically, it is partial tangle defines that a non-zero value. Now let us see what this type of what exactly, when we are plotting this in simulating this in the experimental aspect, what exact result does it give? Now, in the third cases, we will discuss with the concurrence fill. This concurrence fill is a very interesting property of entanglement measures, which provides the entanglement in geometrical aspects. Consider this ABC as a three-party system that is given by this, uh, sorry, that is given by this triangle. Now, if considered there is an entanglement effect between A and they are entangled, considered. And if they are entangled, then the sides of this triangle gives the entanglement measures between the any two flavor. And this area of this triangle provide the measure of the tripartite entanglement. More the area of the triangle, more the tripartite, genuine tripartite entanglement is present. Lesser the area, less the possibility, more the possibility of having the bipartite type of entanglement. And if this area becomes zero and boils down to a line, then it shows that it is just a bipartite system. And if it is very, and the separable state is given by this simple dot. So this is a very interesting visualization of entanglement geometrically. Now what we do is that, what we did is that we first mathematically define this particular formula which we are defined for the neutrino cases, which gives the expression of the concurrence fill for the neutrino. And this is a mathematical, completely mathematical formulation. We have not yet considered any experimental aspect of it. Now we have this machinery in our hand. Now we will justify this through the experimental aspect. How we can do that? We considered a particular experimental setup. There are various neutrino oscillation experiments going on all over the world. And we considered one of the long baseline experiment, which is a future long baseline experiment that is called the Dune. And what we did is that we have simulated in a software that is the general long baseline experiment simulator globes for this particular experimental setup for the Dune. So Dune has a baseline length of 1300 kilometers starting from the Fermilab in Chicago, and detector is in the Stanford Underground Research Facility in South Dakota. So neutrino actually travels 1300 kilometer distance from production to detection. And what we have observed that if we consider this particular experimental setup and we consider this mathematical formulation, then after simulating in globes, we get a clear signature of the oscillatory nature of the concurrences. And here we can see that concurrence is actually having a value of 1 at that point, uh, where the concurrences, this green and blue line is actually achieving a value of 1. So when the concurrence is achieving a value of 1, it depicts the maximally entangled state. So maximally entangled state is appearing between the this tau and mu flavor, neon and uh, tau flavor actually. And however, when we separate out the electron flavor mode, so this is the electron flavor mode if we separate out. So the entanglement between the electron and other two flavor is not as much as the muon and tau. So this depicts that neutrino do execute maximally entangled state, and they are at the maximally entangled state are achieving between the muon and tau flavor. So if we consider now let us consider the other entanglement effect, that is the concurrence field. In the previous slide, we have observed the three type of we have considered this three dot A, B, C as muon, electron, and tau, and where we have seen these three sides of the triangle from this table is non-zero. See, at 2.6, it is non-zero, and 0.8 as well. It is very much large. These three sides are profound, 0.8. And although at 1.3 GeV, we can see that there is no this all the sides of that all the sides of the this concurrence triangle vanishes and goes to zero. And this is because at 1.3 GeV, all the flavor state is actually goes to zero. Only the muon flavor state, I have not plotted it. I may have plotted it in other plot as well, I guess. But here actually what is happening that at 1.3, all the flavor state goes to zero. Only the muon flavor state exhibits. Only the muon flavor state exists. So at this energy point, it actually behaving as a separable state. So, but I have to mention here that all the neutrino oscillation experiments measured all the oscillation phenomena and measurements has been done on first oscillation maxima. What is the first oscillation maxima? Where the first appearance probability of electron neutrino becomes the largest. And this for this dune experimental setup, this appeared for 2.6 GeV and 0.8 GeV. This is the first oscillation maxima, and the second oscillation maxima, where the experiment is most sensitive to the measurement procedure. And we can see at these two energy levels, this concurrence triangle, the value of this concurrence triangle are non-zero. However, 2.6, we can see that it is one of the concurrent side, one of the sides is almost becoming negligible. Now let us come to the concurrence field. Now, what we can see that concurrence field also gives us the same kind of signature. Here in this plot, we have plotted the concurrence field and the perimeter of the concurrence field. Actually, the concurrence field with respect to the energy of the neutrino, and this Q is the perimeter of the triangle, and CF is the concurrence field, the area of the triangle. And this dashed line is for the vacuum, and solid line is for the matter. So why we are considering vacuum? So we wanted to observe whether when the neutrino is traveling in the vacuum, if they are having the same kind of entanglement effect or not. So what we observe that yes, in both the cases, they do have the same kind of entanglement signatures with non-zero value of entanglement measures like concurrence and concurrence field. And what we get that we have plotted this concurrence triangle for all this four energy range. First oscillation maxima 2.6 GeV, second oscillation maxima 0.8 GeV, maximally mixed state where we are observing 1.7 GeV and uh, almost separable state that is 1.3 GeV. And what we observe is that, see, 1.7 GeV is giving us the maximal area of the triangle. This gives the signature that the neutrino do exhibit W kind of state. I mean W type of entanglement. And in 2.6 and 0.8 GeV as well, we can see that it is having a non-zero value of this concurrence field triangle. With although the area becomes lesser than the 1.7 GeV, so this signifies that throughout all the energy range, neutrino do exhibit W kind of entanglement. However, when the oscillation probability, when the appearance probability means the other two flavor apart from the probability of getting other two flavor apart from the initial flavor. That is, if we consider initial flavor state as mu, then the appearance probability will become the appearance probability of electron and tau flavor. So when the appearance probability of electron and tau becomes zero, then we will get a separable state, biseparable kind of state at 1.3 GeV. This entire analysis gives us a clear signature of W state inequality, W state entanglement, and which is morely justified when we plot this W type of W state inequality. So what does this W state inequality says us that if a particular state or if a particular particle satisfies this inequality condition, then it exhibit W kind of entanglement, not GHZ kind of entanglement. And what we have seen that it actually for the neutrino, they exhibit this, they clearly satisfy this W state inequality, particularly at that energy point where the system is maximally mixed, that is 1.7 GeV. So this carries the clear signature that neutrino do exhibit the signature of W type of entanglement. It does not exhibit GHZ type of entanglement. It exhibit the entangled state and exhibit a mode intra-particle mode distributed entanglement for the three-flavor neutrino oscillation. And uh, this entanglement is not continuous throughout. They also exhibit a biseparable kind of signature when the appearance probability goes to zero. Now the question is how we can use this uh, entire concept of entanglement for measurement in the measurement process. Well, I have to say that there is a very distinguished problem in the physics we all know is the matter-antimatter asymmetry of the universe. And since our world is matter dominated, now for the neutrino case, where does this signature carries this matter-antimatter asymmetry? This matter-antimatter asymmetry is carried by the delta CP angle that is embedded in the UPMNS matrix for the three flavor neutrino oscillation. If delta CP angle is zero, then there is no CP violation. If delta CP angle is non-zero, then there is a CP violation. So, what is the CP violation means is that consider the neutrino is oscillating from neon flavor to the electron flavor. Now, this has an oscillation wave of particular frequency, oscillation frequency. Similarly, if we consider the anti-neutrino sector, since it is lepton, do have the anti-neutrino as well, which has been, we can observe it in the beta decay, where antineutrino emitted, usually it emits antineutrino. So when for the antineutrino sector as well, it exhibits this oscillatory property. And the rate of oscillation from uh, a muon antineutrino to a muon electron neutrino, if they are equal to the oscillation probability of uh, electron neutrino to muon neutrino to electron neutrino, then there is no CP violation. However, if they are not equal, then there is CP violation. And this is what we call the CP violation in neutrino sector. And why, when it will be non-zero, when the delta CP angle will be non-zero. If delta CP angle is zero, then there will be no CP violation. Now the question is how we can incorporate this entanglement effect in measurement of this CP phase. Now this oscillogram plot, what it implies that we have plotted in the y-axis energy and x-axis is the delta CP angle and the z-axis, that is the CF, defines that this color variation actually. So the areas in from this plot where it shows the maximal color gradient in width of CF when we are varying delta CP, at that point when we can say that a particular uh, observable is sensitive to uh, that particular phase angle. So what it means that we are considering CF as a CP phase witness, concurrence fill as a CP phase witness, and CP, if the sensitivity will be the maximum when there is maximum gradient in the color in variation of when we are varying the CF with delta CP. And we can observe that this maximal variation is observing at 0.8 GeV, right? Because there are also other region as well, I do agree. But we are focused to observe this phenomena, this particular analysis for 4 energy beams, 2.6, 1.7, 1.3, and 0.8. At 2.6, we are observing a variation. However, it is not that much sensitive. At 1.7, also we are observing, but 1.3, there is no variation. It is almost a band structure. However, in 0.8 and 1.7 as well, we are observing this variation. And since the particular experimental setup that we are considering, for the dune, 0.8 GeV energy depicts the second oscillation maxima. So, implying the concept of entanglement in the physical experiment, and considering CF as the concurrence fill as a entanglement measure, second oscillation maxima is the most sensitive region to have a optimal sensitivity of this CP phase. So this way, this is the bottom line of our work. So as a summary, what I can say that we have constructed the single particle multimode entanglement structure for the neutrino, and in the a 3-qubit framework was also developed, quantifying the different entanglement measures like tangle, partial tangle, concurrence fill, and we have expressed it the experimentally measurable in terms of the experimentally measurable oscillation probabilities. And what we have observed that entire formulation has been done with the density matrix formalism, this mathematical expression of concurrence field and all. And what we have observed that after simulation in globes for dune, we observe that neutrino do exhibit W kind of entanglement. It does not have Z kind of entanglement. It also exhibits a monogamous nature, and also it it satisfies this W state inequality. And ultimately, if we consider as CF as an entanglement witness, then it is most for the experimental setup of Dune, second oscillation maxima, observing the phenomena of entanglement and employing the concept of entanglement in oscillation parameter measurements, second oscillation maxima plays a most profound role in delta CP measurement. So this is the bottom line of my talk. And if you wanted to dig out more, you can go through this work, which has been recently published in Ph.D. Thank you.
I have one question. So,
Yeah,
yeah, thank you for a very interesting and informative talk. So, in your talk, if I understood correctly, you have considered unitary approach or unitary evolution.
yes,
So, if we bring non-unitarity
yes.
in your quantum system, what level of impact we may expect on the degree of entanglement?
Absolutely. Thank you very much for this question. Yes, there is, there might be non-unitarity effect, that is PT asymmetry, decoherence, and also neutrino decay. And what we observe that it is still in progress, our work. Uh, this non-unitarity makes a very profound role in the uh, this CP phase measurement. And also, if there exists non-unitarity in terms of neutrino decay, it actually, I mean, deduce the amplitude of a neutrino oscillation. But I must say that there is no clear signature of neutrino decay yet we have got in the experimental level or the decoherence. Yet we have not observed it since neutrino exhibit only the weak interaction. So mostly neutrino do unitary evolution. But yes, we should consider pros and cons. So we have to consider we are working on that for the non-unitarity effect.
Thank you.
Any other question? Uh, Ms. Banerjee, I want to ask a question, very basic questions to me. Maybe
Yes.
it is very simple questions to you. I want to understand your perspective on what is the difference between entangled state and non-separable state. Are they same or is there any difference?
Entangled state and non-separable. Okay, so there are three kind of states: separable state, biseparable state, and entangled state. So entangled state, if the state is separable, what we mean by the separable state? Consider a simple state. Psi is equal uh, 1 1 plus 1 0 state. Kate of 1 1 plus kate of 1 0. Now from this state, you can take out this 1, kate 1 out. So you can rewrite the state as kate 1 direct product of k2 within bracket kate 1 plus kate 0. Right. So this is called a separable state. You can, this is a this is also a superposition state, but it is in the form of the separable states. But however, if you have a state like this, uh, say 1 0 plus 0 1, kate psi is equal kate of 1 0 plus kate of 0 1. So from this particular state, you cannot take either one or take zero out and write it in the direct product with the other state, like you have done previously. So this particular state is the non-factorizable state. You cannot take out any other state, any one state out and write it in the direct product state. So this particular state is called the entangled state. Both of them are superposition, but this is the entangled superposition, and that is the previous one is the simple superposition, like separable states.
Is it similar to weakly correlated and strongly correlated?
Entangled, the definition I have given in the second case, 1, 0 plus 0, 1. If they have a coefficient 1 over root 2, then it is called the what you call the strongly correlated system.
Strongly correlated. Yeah.
But if they have in general, the coefficients are different, like C1 or C1 10 plus C2 01. So depending upon the value of these coefficients, they can be strongly correlated or weakly correlated. However, they are entangled.
Okay. Is the non-unitarity leads to non-Hermitian also?
No,
Unitarity.
Non-unitarity.
In the common knowledge, almost all operators of the quantum science is the unitary operators, isn't it?
Absolutely.
And also, if you talk about non-unitarity, what physically it means?
Physically, non-unitarity means that there is a dissipation in the system.
Okay.
All the quantum operators are the coherent superposition. Coherency is the key, is the foundation of the quantum mechanics.
Okay.
But if there is a loss of coherency, coherency also there is mathematical formulation for defining the coherency, like L1 norm.
Okay, thank you.